Ladies and gentlemen, please join me in welcoming Executive Vice President of Microsoft, Jason Zander.
Appreciate it. And thank you so much, Governor Dr. Pines. I really want to thank the governor personally for his leadership here. He has definitely been fully engaged with us, has great ideas. It's been a fantastic partnership to go get all of this set up. It's exactly the kind of partnership that we like to have, because what we're interested in doing, we share these same goals. We want to bring along PhDs, we want to bring along machines, we want to further quantum science and engineering. And you need partners that are kind of equally involved and engaged in that. So once again, thank you so much. We're very excited to be here, and we're looking forward to it. One of the things we need to do is we want to absolutely accelerate this ecosystem. What's really great about this conference is we know how fast things are moving. And this center and the work that we're now doing to bring PhDs into it is going to be a core part of that. In fact, if I look at the momentum that is out there, this is just the last 9 months just for Microsoft, not even some of our colleagues from other companies also working. In that time, we announced our Majorana 1 chip that we have, which has a new state of matter behind it. It's actually involved taking a theory from 1937 and doing the applied physics to prove that you could actually demonstrate that theory. But not only that, turn it into a qubit and then multiple qubits and turn it into a new form of compute that's fast and it's small and it's scalable. And these are the sorts of machines we'll be able to bring into the new center that we have. In addition to that, we announced a 4D geometric error correction code. Error correction is super important. We're going to have to get to the point where if we want to use, especially quantum computing for its full potential, we have got to get to fault tolerance. That means we have to do logical qubits. Those are ones that essentially sit on top of physical qubits, but the most important thing is they give you reliable outcomes. It's the next generation that we're going to have to get to. So we've also announced the world's largest logical qubit machine, which will have at least 50 qubits, about 1,200 physical qubits underneath when we go forward. So these are just in the last 9 months. And like I said, there's a huge amount of momentum that is coming through, and it is moving fast. So it's never been more important that we can establish a center like this to go work on that kind of excellence. And it's not going to be just any one company. Some of the things I just discussed were actually much more about the hardware. There's lots of modalities, there's lots of different types of computational work that's been done. And in fact, at Microsoft, we are not just building our own chip, we're also working on the full stack with a lot of partners. And with that, we hope to solve the world's hardest problems. In chemistry, material science, pharma, drugs. These are all the ones that we talk about, but at the end of the day, you have to ask, how are we actually going to do that? Because quantum computers, that's the promise they're going to give us. We're still going to have tons of CPUs, tons of GPUs. You know, like, how do we solve these problems going forward? Quantum is an accelerator for that. And to solve those problems, we need all of that technology to come together. In fact, that future is actually hybrid. Right? We're still going to be using high-performance computing. We're going to increasingly use AI in science. In fact, we're already discovering novel molecules, new materials. We did a liquid immersion coolant that is PFAS-free recently. Actually used that technology and synthesized it, proved that it actually works. And that's before we have a quantum computer. When I have a high-scale, utility-scale quantum computer, it'll get even faster. And so that's the types of problems that we want to solve. These are the sorts of things that we're going to be tackling directly with this new initiative. And again, PhD to PhD, bringing in engineering companies and working with partners across the industry. That's where the future is going to come from. That's where we're going to be able to unlock some of these new problems in science. And if I think about the long tail of this, if we can do a great job inventing new materials and new ways to do things, you can actually follow that all the way through that supply chain. Eventually, that means we can change manufacturing. We can change the way in which industries are going to operate in the future. That'll also create new potential. So in the near term, lots of PhDs, lots of engineers. We need those folks. In the long term, I expect us to see and have impact where we can create even more jobs, more skilling, more things that will actually allow more people to contribute. And we need people, because we have to continue to educate and get the most advanced folks, and being able to do it in a center like this is a core for what we're trying to do. But like I said, no one company, I think, is going to be able to do this alone. A lot of the conversations we'll have here at QWC will be about the different modalities and how fast are people going and how many qubits do you have. That's kind of down at the hardware level. Super important, we have to have that. But of course, there's also companies that are tackling these hard problems at the workload level, the library level, those sort of things that do need to get done. And that also means that I don't know that there's going to be just one chip that rules them all. There's going to be multiple. In fact, we want to partner with them. And you'll see many of the other quantum chip modalities that we're working with, architectures that are there. It's our goal at Microsoft, once again, to help the ecosystem be able to move along. And that means it may be my chip, but it might be other chips. And it's going to be everyone coming together, because that's the only way we're going to solve all of this work and get the new workloads up and running. So it's super important for us to have the partnerships. And like I said, you see some here, we have more that are coming. And again, the important thing to me with the new center that we are announcing today is that we're going to be able to bring that technology in. We're going to bring our own experts in. We're going to be able to actually go do applied research with everyone and figure out how to get this ecosystem moving as fast as possible. So that's what I'm really excited about, and I want to thank the governor and his team. Been fantastic to work with. It's really super exciting for us to go drive that new innovation going forward. So there's a lot of new stuff to happen. So what I want to do is give you a little bit more detail and explain a little bit of what we're going to be doing in the center and that kind of work. And I'm very pleased to welcome Charlie Tahan from our team. Dr. Tahan, many people in the community know Dr. Tahan with his extensive experience both in academia but also in the government as a member of our team. And so, Charlie, take it away. Thank you.
Thank you, Jason. Thank you, President Pines. Thank you, Governor Moore. It's a real honor today. It marks a lot of progress within Microsoft Quantum and building our quantum ecosystem. And I'm really excited to share a little bit of our thinking and what we're planning to do with our new quantum center in Maryland. As Jason said, we want to build and provide our partners and customers the best computers in the world. And that has to eventually include quantum computing. It is the foundational shift in information technology. It will be, important to our society. What that means in practice is, this is the vision. We need to build it, right? We actually have to build a computer. One of the reasons I came to Microsoft is that the company aspires to build the world's computer, at the biggest scale imaginable. When you think about what it takes to actually do that, to realize that vision, from the hyperscaler workloads that might span multiple data centers, to the developer tools, languages to enable the community, to the real-time operating system and orchestration across machines across the globe, the actual silicon and future chips that have to power that immense machine. For a kid who became a scientist to change the world, corny but true, it's hard to think of a better mission for your life that will not only give you the biggest challenges we have as scientists, engineers, entrepreneurs to tackle over our lifetime, but also could have the biggest impact on our society. So our mission, and I started off as a physicist, but I'm becoming more of an engineer day by day. Our mission is to build these next generation computers. And when you look at each level of the stack, there are immense challenges to solve across the entire layer structure, from the applications all the way down to the physical computing instantiations of the machines. And from the perspective of a cloud company that builds the biggest and best computers on the planet, a quantum computer fits very nicely into this architecture. We have systems that use CPUs for general compute. We have accelerators that use GPUs or FPGAs or ASICs custom chips that are designed specifically for some problems like AI. Quantum adds another accelerator that provides a whole new type of computing that really completes what information processor is, but fits very well within the overall structure of how you build a high-performance computer. it also adds a whole bunch of new layers of things you need to solve. Everything from a real-time engine or operating system that can very quickly correct errors on many qubits that are extremely delicate, all the way to the new software and algorithms you need, and to obviously the qubits exist themselves, which are in many modalities. And we just don't know yet what qubit modalities, or which several, will go the distance to a useful quantum computer. So when you're trying to tackle a problem that big, how do we get to a useful quantum computer as fast as possible? To me, it comes down to your resources, your ideas and technology, your people and organizations, your tools and infrastructure. You need to amass them together at critical mass to make a difference, but that's not enough. You need to focus them also on the right problems, on the problems that will actually make a difference to our users and partners, and to the problems that Jason was mentioning. And at Microsoft, we take a pretty rigorous approach to truly trying to understand how big a quantum machine it will take to beat out, our best high-performance computing. And as AI gets even better, that capability that the classical, the world has built over the last 100 years is also getting better. So we need to really understand what is the target, the guiding light of a machine, that if we could build that, will really change the world. And despite rapid progress in algorithms and quantum error correction, some even over the last few months, we still think you need a pretty big and complicated machine, a fault-tolerant machine, hundreds of thousands of qubits as that guiding light. Hopefully, of course, from where we are today, hundreds to 1,000 physical qubits, to that goal, there's many opportunities for discovery. But that is the guiding light that must drive us, a true fault-tolerant quantum computer. And that's a hard goal. I think there are three forces that kind of guide our approach at Microsoft to leapfrogging and getting to that goal as quickly as possible. We need to think about how we can disrupt and skip the line, of technology development. One, can we find qubits or quantum plane technologies that have unique superpowers, things that let them be easier to build into systems, for example? Two, how do we build architectures that fundamentally scale? Meaning we know quantum is different from your normal computer. Instead of, one line per 1,000 or 10,000 transistors, for quantum computers, you need multiple wires or multiple laser beams to control a single qubit because of their delicate nature and quantum error correction, the need for quantum error correction. So it creates this huge I/O problem, in addition to all the other problems of they have to be cold, they have to be in vacuum chambers. So you really need to think about architectures that can scale to that large size from the beginning if you want to get there as fast as possible. And the third thing is, how do you be relentless in reducing the resources you need? Everything in the system, from the number of the qubits, the number of wires, the size of the algorithm you need to run, the size of the fridge. How do you be relentless in reducing those requirements so that you can produce an economically viable thing at the end? And to me, these three great forces, are what will let us, as a community, address the two big questions in our field. Because we talk about competition a lot, competition between qubits, different types of qubits, competition between companies, but we're not competing with each other, right? We are competing with 100 years of classical computing innovation, algorithms that have been designed to approximate nature and chemistry and material science extremely well to get the problems we need on the computers we have, and computers that have been driven by an economic engine that the humanity has never seen before. We're competing with that as a field. And the two things we need to answer are, how do we, what do we actually need to build? What is the computer that is going to create a market and that economic engine for this field? There are inclinations, we are learning things that AI will accelerate that quantum could potentially help classical AI, and I think we're going to see a lot of results on that this year, but we still think you need a pretty big computer to make that difference. But that is number one question. What do we need to build to create a market? Second is, how do we get there fastest? How do we bring the collective experience of everything we've done before, in our society and technology to bear to build the simplest system possible to make that goal a reality? To me, those are the two fundamental questions as a field will make us win or lose. And in that vein, when you think about Microsoft, our core value is the platform, and that really means partnerships. At every layer of that stack, there are many different technologies, many different companies, many different people that need to come together to constantly making it better to realize it. Many different technologies make a computer, and that is no different in quantum. We don't know what the future will hold. We do know that it will be a complicated machine with a lot of different technologies that are needed. So for us, building a quantum computer means creating partnership. That is fundamental to the goal itself. And with that, it gives you some idea of why we have chosen to partner with the state of Maryland, the governor of Maryland, in the Discovery District as part of the Capital Quantum Initiative, because what is needed for us to answer these questions as soon as possible is partners who understand the journey we're trying to take. We need to answer fundamental questions, we need to move quickly, and we need to, frankly, just build it and see if it works. And a natural partner for us has been DARPA through the Quantum Benchmarking Initiative. They have a long-term vision of how do you build a utility-scale quantum computer, and what does that really mean? That is a very natural, there's a very natural synergy with our philosophy. So our first partner in the new center will be DARPA. They will have access to one of our topological qubit systems as part of the QBI program for their test and evaluation team to poke and prod and learn from and evaluate. We're very excited about that. And we'll use this unique space, which will be a functioning lab, it'll be a functioning development site for Microsoft engineers, but we'll also have areas to collaborate with the government, to collaborate with our partner companies across the supply chain, other quantum companies, integrate their technology into our operating system and computing stack to help accelerate their time to market, and also with the university and the academic ecosystem, because we need not only to train the next generation of people, but we need ideas. Like to leapfrog what we need to do, we need the best ideas as fast as possible applied in practice. So with that, we are super excited. I want to thank the state of Maryland, the amazing people on the Maryland side who made this possible. I want to thank the team at Microsoft, that a lot of people have to come together to get a center like this, a new partnership like this formed. It's a new type of public-private partnership. Some of the nascent DC team is here in town looking for houses, so we're super excited to move in and get started as soon as possible, and thank you all.